Conservation of angular momentum is a very important law when it comes to the conservation laws of nature. We know that there's conservation of energy, there's conservation of linear momentum, and finally, there's conservation of angular momentum. When we look at different systems, we want to make sure that all of these are conserved. Specifically, when we're looking at rotating systems, we want to watch to make sure that the angular momentum is conserved in an isolated system. And as the moment of inertia changes, this will affect the angular velocity. So once again, angular momentum. If the net torque is zero by Newton's second law, the angular momentum remains constant. It is conserved. And essentially, the angular momentum at the beginning of the problem is equal to the angular momentum at the end of the problem, again, as long as there's no torque on the system. So conservation of mechanical energy, conservation of linear momentum, conservation of angular momentum are the three important conservation laws. Obviously, for angular momentum, we're concerned with the rotating bodies. So mathematically, we first of all have to make sure that there are no external torques acting on the system, that the total torque on the system is zero. Here we can set Li equal to Lf, since torque is equal to the change in angular momentum as a function of time. If that change is zero, this quantity is going to be conserved. A better way to write this expression is to say that I initial times omega initial is going to be equal to I final times omega final. So let's take a look at some particular systems where momentum is going to be conserved. One of them is the case of the somersault. Now, finding the moment of inertia can be really complex for a complicated body like the human body. But if we look at just general results, a human body, when they're in the vertical position, what we might call the pike position, has a moment of inertia of about 14 kilograms meters squared. I should say the extended position, because the pike position would be when they extend their legs and their arms away from the center of motion. That moment of inertia drops to 8 kilograms meters squared for the average person. And then pulling their legs in, they're putting the mass closer and closer to their body. The moment of inertia can drop down to 6. Then finally, in a completely tucked position, where as much of the mass is concentrated around the center of mass as possible, there we get a moment of inertia dropping down to 4. So if we look at this, we can see that our moment of inertia for our body, when rotating in the horizontal direction, and when somebody does a somersault, they're going to be rotating along a horizontal axis, their moment of inertia can drop down by a factor of 3.5. And that's going to have very important effects on the rate of rotation. So let's take a diver who's going to just do a single somersault in the air and then enter the water. They start out with their body essentially upright. So here we're having nearly the maximum amount of moment of inertia, right around 12 or 14. And then they push off the diving board to create torque. Now, this is actually done a number of different ways. Usually what has to happen is we have to move the center of mass a little bit forward from the diving board. We push off the diving board. This creates a slight moment arm between the center of mass and the line of action of the force, and we're going to get rotation from that. So in this particular case, she creates this downward force as an equal and opposite upward force. This isn't so represented because, again, she's going to want her center of mass a little bit forward. So the work coming from the upward force of the board is going to create some translational kinetic energy, but also some rotational kinetic energy. But she's going to start out with some large moment of inertia, okay? But in order to rotate faster, because initially she's going to start with a fairly low angular velocity, she can then tuck her body. And again, if you're dropping your moment of inertia by a factor of 3.5, in order to conserve this, if I is divided by 3.5, we've got to multiply the angular velocity to keep I omega, the angular momentum, constant. So she's rotating 3.5 times faster at this peak right here. That allows her to change her orientation, make one full revolution, actually make a revolution and a half. And right before she starts approaching the water, she'll then flatten out. This is going to do two things. One, it's going to allow for a smooth entry into the water, but it's also going to slow down the rate of rotation, because if you're going into the water rotating, it's going to be very, very difficult to control how your entry there. Now, again, we can just look at this way. We can look at the somersault very simply as, again, I omega is going to be constant. We do create a torque initially. Again, this is a little more representative because the person doing the somersault is leaning forward. The center of mass is now in front of the base, okay? Pushing down increases the normal force, so that increases even more torque. So the upward force from the floor, the normal force from the floor, counteracting the downward force from the legs, is going to create an upward motion, but it's going to also create a rotational motion. Okay. Oh, the other thing that's happening here too, we can't say the force is exactly straight up. The force is sort of at an angle here. So she's creating sort of a parabolic motion for her center of mass, but at the same time, some of that energy is being used to create torque to gain this rotational kinetic energy. And again, as she tucks, her angular momentum is being conserved. She's going to rotate faster, but that's also not going to increase the rotational kinetic energy. As we make omega larger, okay, for a given I, it's also going to increase the rotational kinetic energy, but both are still balanced in this particular case, because as you're pulling yourself in closer, you can still conserve your energy in that particular situation. So again, you can see a handspring right here. Again, the body's extended during the handspring. We're creating torque in this particular case, pushing off, okay? Pushing off while the center of mass is away. This creates both rotational motion and translational motion. And as we go up in the air, body's put into a more compact, lower angular moment of inertia state. So the angular velocity increases, allowing them to rotate quickly, and then extending the body to get back control to stick the landing. And again, you can see this right here. The total angular momentum remains constant during the entire trip, okay? During the entire trip, the angular momentum doesn't change at all. But during the beginning, we have a low rotation rate, high moment of inertia. As the two trade off, the angular velocity increases, the moment of inertia decreases, and the body starts rotating faster. And again, you can see that in this particular case, here the person's actually rotating backwards. Again, we're going off a base, but by leaning backwards and pushing off at the same time, this creates torque in the opposite direction. So they're going to rotate counterclockwise in this case. They speed up the rate of rotation at the top of the arc. And then finally, notice what happens here. They're rotating very quickly. They extend their body, rotate slower here so that they can, again, stick the landing. So these acrobatic type moves are really about controlling your rate of rotation by controlling how compact the body is. If you want to rotate faster, obviously you pull your arms and your legs in. If you want to rotate slower, you extend them outward. And you can really control the rate of rotation in these acrobatic moves. If you time it correctly, you can get the proper orientation when you make your landing. So this is really quite a skill to do so. If you over-rotate, you're going to go beyond an upright position on your landing. If you under-rotate, your tips of your ski is going to hit first, and that makes for a very uncomfortable and possible crash at the landing. We showed this image before when we were talking about center of mass. And as we see this motorcycle take off again, they're doing the same thing that the ski jump did. They're leaning back to create a large, a large torque here. Additionally, this back wheel is also creating torque on this. So their moment of inertia is pretty constant from here to here. Their angular velocity, again, is in the counterclockwise direction, but watch what happens as the biker pushes off the bike. They're right here, and notice the orientation of the bike rapidly changes as they push away from the bike, and they've essentially created a condition where the bike starts out rotating this way in the counterclockwise direction, and then after they push off, the bike starts rotating in the clockwise direction. So there's a transfer of angular momentum to basically, get the bike to land one way, and for the rider to land feet first. Now, again, we can rotate about many different axes. In the first cases, we were talking about rotating around a horizontal axis, but we can also rotate around a vertical axis for something like a pirouette. Again, here's the moment of inertia for the horizontal axis, fully extended, completely in a tuck position. And now we look at the same for the vertical axis, but here you see that there's much less of a moment of inertia along this axis because there's not as much mass far away from the axis of rotation. Here, the distance between the center of mass and the head and the distance between the feet and the center of mass create a very large moment of inertia. But here, the maximum distance is really between the tip of the hand and the center of mass, and that's going to be less than what we have in the other case. Plus, your arms and your legs tend to have much less mass away from on their ends than the trunk of your body. So in any case, arms and legs fully extended, moment of inertia is about 3 kilograms meters squared. Again, for an average person, smaller people obviously would have less, larger people would have more. And as we go to different positions, again, with just the arms extended, we drop to 2 kilograms meters squared, and with the arms both in, we go to 1 kilogram meters squared. So you've probably seen the demonstration where somebody's rotating on a platform, and they pull the masses closer to the body, they start spinning faster, or they push the masses away. And again, I omega is going to be conserved. So if I make my I smaller by pulling my arms in, I'm going to spin faster because I omega, I's gone down, so omega has to go up. Here we see the case of a pirouette. We see a skater pushing off one skate. They begin to rotate. As they bring their arms closer to their body, the moment of inertia drops in 1/2, so they'll actually double their angular velocity in this particular case in order to slow them, in order to conserve that quantity. Now, in nature, we have many examples where conservation of angular momentum is very, very important. One of the most extreme cases is the death of a supermassive star. Now, our own sun will eventually shrink to become a white dwarf. At least the inner part, the core, will shrink to become a white dwarf, while the outer atmosphere will be blown off into space. When that happens, the white dwarf that forms will be about the size of the Earth. The sun spins roughly about once a month at this point. If it contracts to become a white dwarf, it will begin to spin much faster, taking probably less than a day to spin on its axis. For the most massive stars, their core contracts much more than the sun's core is going to contract. Instead of collapsing to become a white dwarf, which is just degenerate electron matter, it is going to contract, as its name implies, to become nothing more than a ball of very heavy nucleons and neutrons. The electrons and protons, for the most part, are going to merge to make neutrons. So we have got this big ball of nuclear matter, which at one point was heavier than our own sun, and now is only about the size of the city of Manhattan. So what happens when this takes place? Well, in any of these supermassive stars, they're going to keep fusing lighter elements into heavier elements until we have nothing left but iron at the very center. Up until this point, it's been an exothermic reaction. It gives off heat, the heat supports the overlying layers of the star, and the star can continue to exist. But when the iron core begins to fuse, that causes it to lose energy. It's actually an endothermic reaction when we try to put the iron nuclei together. And this causes the core to collapse nearly at the speed of light, leaving all the overlying layers to fall inward. The star implodes and explodes at the same time. The core, where there's a tremendous amount of mass, is going to fall inward. Overlying layers close to the core are also going to make their way inward and collapse onto this very small ball of neutrons and other material. The outer layers will basically blow out into space. So you have conservation of momentum really happening in opposite systems. The outer layers are going to expand outward, increasing their moment of inertia. So the outer layers, which were rotating, many of these very massive stars rotate much faster than our own sun, on the order of maybe days instead of a month. But those outer layers will start rotating slower and slower as they expand out into space, as the supernova blasts these outer layers away from it, while the core will spin up. It'll spin faster and faster and faster. And in addition to concentrating the mass, it concentrates the magnetic field that basically accelerates particles and produces a type of radiation we call synchrotron radiation. So we have this very rapidly rotating neutron star, which is pulsing energy into space on the order of milliseconds when they first form. Now, Jocelyn Bell Burnell discovered these radio pulses from these pulsars when she was doing her graduate work. And as a result, her advisor got a Nobel Prize for this, but she eventually was awarded an even larger monetary prize later on for an award that was basically designed to honor her and the fact that she was skipped over for the Nobel Prize. But she's the one who, during the very advent of radio astronomy, discovered these rapidly rotating bodies to prove, in fact, that yes, the heaviest stars in the universe end their lives as these massive supernova explosions, where the core of them implodes to become this rapidly rotating body. Now, just to give you an example, what would happen if the sun would become a neutron star? First things first, we have to talk about the fact that not all the star collapses into the neutron star, okay? Quite a bit of the matter is blown into space. So that is going to take with it a large amount of the angular momentum that the star originally had. But let's say if we took our sun, or we took the core of a star, which was about the mass of the sun, and allowed it to collapse into something no bigger than a neutron star, what would happen? This is pretty representative of what happens in these massive stars, which are many times the mass of our own sun. Well, the sun has a spin rate of once every 25 days. And basically, with a radius of 7 times 10 to the 8 meters, if the sun were completely a homogeneous sphere, which it's not, it's denser in the middle, if it were to collapse down to 12 kilometers, which is about the radius of a neutron star, it would be spinning at a much higher speed. So initially, let's say its initial angular momentum is Li. Its final angular momentum is going to be Lf. And I times omega is going to be on the left-hand side of the equation, where we have our initial moment of inertia times our initial angular velocity. and I omega final is going to be on the other side. Now I is going to become very, very much smaller, and omega f is going to become much larger. So the angular momentum of a spinning sphere is I omega, okay, which is I times 2 pi times the frequency, okay? So for a sphere, which is homogeneous, we have about 2/5 mr squared times 2 pi f. That means that my I omega is going to be 4/5 pi times the mass. The mass is going to change. The radius is going to change, the radius squared times the frequency. So if I put this into this equation, what do I get? The 4/5 cancel out with 4/5. Pi cancels out with pi. We're going to assume that there's no mass loss, okay? That's not the case for these dying stars. A lot of the mass is being blown into space. But let's say we're taking a part of the star, which is about the mass of the sun, okay? All that collapses from an initial radius of 7 times 10 to the 8 meters. That's much bigger than what we'd have at the center of the star. So this is going to play a role too, to a final radius of 12 kilometers. If the sun were to collapse, it would be rotating 160,000 rotations per second. We don't see this with neutron stars because, again, we've made a very crude model for a collapsing neutron star. We took our sun and we collapsed it to the size of a neutron star. Honestly, one solar mass of these very massive stars is actually much more compact, so it's not going to spin up to the same degree. I think minimum solar mass would probably be about 20 solar masses for this to undergo a transformation into a neutron star and blow up as a supernova. So the fastest pulsars that we generally see are about the millisecond range. This is sort of getting to the microsecond range, probably about 2 orders of magnitude too high. So again, supernova explosion is a very dynamic process where a lot of the matter is being blasted into space, but we also have this collapsing magnetic field, which when the star is very rapidly coming together, when the core is collapsing, this magnetic field is going to cause a tremendous amount of drag for the core and slow it down very, very rapidly. So again, very important conservation of momentum example right here, which was actually proven by an experimental observation of these neutron stars. We call them pulsars because when we see them, we view the beams which sweep out in space, just like our Earth's magnetic field. The magnetic field of the neutron star is tilted on its axis. As it sweeps past us, we get a pulse for one of the beams that's pointed toward us a little better aligned, and then a smaller pulse for the beam that is not as well aligned with our direction. But again, great example of conservation of angular momentum for our pulsar.